We're going to do some magnetic force sample problems. Let's start off with question number 1. We see here that it says an electron is traveling. Because we're dealing with a charge, our magnetic force formula is equal to Q V B. So that's pretty straightforward for this question, as that the charge of an electron is still 1.6 times 10 to the minus 19 coulombs, times the speed in this case, which is simply 4 times 10 to the 4 meters per second. And then times the magnetic field intensity here, which is given as 4.5 Tesla. Use a second to get caught up. Hit pause if you need. When I punched that into my calculator, I got 2.9 times 10 to the minus 14 newtons. Okay, question number 2. Conductor is 0.35 meters long. It's entirely in the magnetic field. Has a value of 0.22 Tesla. And it tells you the force. It wants to find out what the current. So since this is a conductor that we're dealing with now, we have to use the other formula. Remember, who was the guy who taught electrical circuits down at Elite? His name was Bill. So we have to do a quick rearrangement of that so that we get rearranged for the current, which is I. We just divide both sides by magnetic field intensity, and then by the length which is in the conductor. So the force here was identified as 4.2 times 10 to the minus 2 newtons over the magnetic field intensity, in this case was 0.22 Tesla. And we multiply that by the length in the conductor, 0.35 meters. Don't be thrown off if they put that into centimeters and stuff. So punch that in the calculator and I get 0.545 amperes. So we get to question number 3. A little trick here because now they're asking for acceleration. As soon as you see that at this point of physics, you know that this is in play. F net is equals ma. As soon as they're asking for acceleration, you know that you're going to have to bring that major principle in accelerated motion, Newton's second law of motion, F net equals ma to play. Now it turns out in this particular case, the F net is equal to the magnetic force. There's no resistance, there's no other forces acting on it. So then we first have to find what Fm is using QVB because it's a particle, an electron, which is accelerating, so we use that formula. The other thing that's kind of neat and to be interested, the speed stays constant. So when that charge goes into this magnetic field, it goes into a circular motion. So you got a magnetic field here, it's going to go in a circular motion, but the speed stays constant. Well, if the speed's constant, how is there an acceleration? It's the change in direction. Remember that acceleration is a vector quantity. It's not just the speed, the magnitude of the speed, it's also the direction of it. So really quickly on this one then, it's an electron. So the charge is 1.6 times 10 to the minus 19. The speed of it was given as, I can't see it, 8.5 times 10 to the 4 meters per second. Magnetic field intensity was 0.35 Tesla. So when I punch that into my calculator, here's what I get. I get 4.76 times 10 to the minus 15 newtons. So when it comes to finding the acceleration then, I take that value of 4.76 times 10 to the minus 15 newtons divided by the mass of an electron. If you don't remember this, look it up on your formula sheet. Everybody call 911. Shawty something something on the dance floor. I can't remember what Shawty was doing on the dance floor. Punching that in, I get 5.23 times 10 to the 15 meters per second squared. So, as we like to say, winner, winner, chicken dinner when you're doing it right. It looks like this. Now again, this question is going to be a little more complex. It's an alpha particle, so we know that we're going to use Fm is equal to QVB because we're talking about a particle. We know that this is an alpha particle, so we do know that the Q is 3.2 times 10 to the minus 19 coulombs, double the elementary charge. Magnetic field intensity was given as 0.3. However, we were not given the speed. So we're going to have to find the speed given the fact that we were given its voltage, its potential difference. So what we're going to do, remember this is a small v for speed, potential difference, delta E over Q. So delta E is equal to V times Q, 2000 volts, times the charge of the alpha particle. Again, don't get confused with a proton or an electron. Remember, this charge is 3.2 times 10 to the minus 19 coulombs. And we're going to get 6.4 times 10 to the minus 17. Joules of energy. From that now we can go EK. Sorry, a little sloppy here. EK equals 1/2 mv squared, so that V is equal to the square root of 2 EK over M. It's going to be 2 times that value of 6.4 times 10 to the minus 17 divided by the mass of that alpha particle. Mass of the alpha particle on your formula sheet is identified as 6.65 times 10 to the minus 27. Look that up. To ensure you've got that down, look up to get it down. And from that we get a speed of 1.39 times 10 to the 5 meters per second. So now we have enough information to find that magnetic force. We know that the charge of that alpha particle is 3.2 times 10 to the minus 19, because that's the charge of an alpha particle. Multiply that speed we just found, 1.39 times 10 to the 5. Multiply that by the magnetic field intensity, which again was 0.3 Tesla. So when I punch all that in my calculator, I get 1.33 times 10 to the minus 13 newtons. So make sure that you now hit pause on that video and do all of those calculations yourself to make sure they work. Make sure I didn't make a dumb mistake. A little more straightforward. It's a current carrying conductor now. It's a wire. So whenever you think of electricians, you think of Bill. It's also an electrician currently, Bill Bowering in town. If that's a better way to remember, that's the formula you need. 0.65 is the magnetic field intensity. The current is 0.255. And the length of the conductor in the field is 0.454. Punching that in the old Texas Instrument, I got 0.0752 newtons, or 7.52 times 10 to the minus 12 newtons. Check that one. I didn't do that one ahead of time, so make sure I didn't make a calculator mistake. So this question again is going to be an FM is equal to BIL. However, we're going to have to find our I. So to find our current, We know that that's equal to Q over T. We know the time is 10 seconds, so that's easy enough. But it doesn't tell you the charge going through. It tells you have 2.00 times 10 to the minus 19 electrons. So you're going to take that number of electrons multiplied by the charge of 1 electron, or you could use your picket fence or your factor label method to get your current there. What you end up with is, the beauties of pause for my calculator is I can catch my mistakes. So originally I had on here minus 19, and of course looking up here that was positive 19 for our number of electrons. So when I put that in my calculator, 2 times 10 to the 19 times 1.6 times 10 to the minus 19 divided by 10, I actually get a current of 0.32 amperes. Now I can complete this question. Magnetic field intensity is 0.45 times that number we just got of 0.32. The length in the conductor is 0.375. Putting that in the calculator, I've got 5.40 times 10 to the minus 2. That's my magnetic force produced on this wire, which is moved through that magnetic field. You can watch that video, that TV Ontario video. Well, when do they do that? They're going to do that in an electric motor. Question number 7, it's a wire again, so it's VIL. But we have to rearrange that for I. Magnetic force was 2.75 times 10 to the minus 2 newtons. All that's over the magnetic field intensity of 0.15 times the length, which is 0.75. Putting that into my calculator, I get 0.244 amperes. Now, if you're getting a number a little bit different than that, make sure you've got your master brackets in your denominator, because if you don't, what happens is your calculator is going to take that 2.75 times 10 minus 2 divided by 0.15, then multiply all of that instead of dividing by 0.75. Sounds great. Stay well, folks. I guess you all probably have heard the news by now that the diploma exams have been canceled. So what does that mean exactly? We're not sure. We'll find out as time goes by. I'd still like to, especially if we get back to class at some point in a month or so, 3 weeks or so. I would like to have a comprehensive final at the end if they allow me to. So what I'm going to do exactly, I don't know. If you don't get to come back to class and we have to do a comprehensive final, we'll still try that open book type of styles. We'll make something work. We'll make sure everybody's treated fairly, so don't worry. Have a great spring break. Ciao. Ciao.